from a hole in the middle of the upper disc is blowing against the disc below. To see how we could lift that plastic disc by blowing against it, we've instrumented this plate with pressure taps attached to manometer tubes below. 3 little spacers keep the disc and plate apart. This open tube shows atmospheric pressure. In these tubes, the water level rises when the pressure goes below atmospheric. At the axis, the pressure is greater than atmospheric by an amount equal to the dynamic pressure of the air jet. Over most of the plate, though, it is less than atmospheric and rises to atmospheric pressure at the outer edge. The reason for this is that the through-flow cross-sectional area between the discs increases with radius. This area increase causes a fluid deceleration, and by Bernoulli's integral, a pressure rise. Actually, the viscous forces in the narrow gap are by no means negligible. But in this particular experiment, the mass acceleration forces are generally larger than the viscous forces, and so they govern the shape of the pressure distribution. The subatmospheric pressure over most of the area explains why the disc is lifted. Our flexible wall rig now is in the form of half of a rapid symmetrical contraction. We've discussed the relation between pressure and velocity changes along the streamline. But see how different the pressure distributions are for the two walls. To understand this, we must now think of the particle dynamics normal to the streamlines. This again is our system of streamline coordinates. At this point on the particle trajectory, the radius of streamline curvature is r. The net pressure force acting toward the center of curvature is due to the difference of pressure on these two faces, to the gradient dp dn. Although there is no velocity along n, there is an acceleration, v squared over r, toward the center of curvature. Setting force equal to mass times acceleration, we get Euler's equation of motion normal to the streamline. Here, the important thing is curvature of the streamline. The pressure always increases outward from the center of curvature. In this bend, the streamlines are curved. This is a set of 3 static pressure manometers in the straight section approaching the bend. This set is in the middle of the bend, and this set in the straight section following the bend. In the upstream straight section, the streamlines are virtually straight, and the 3 manometers show no pressure variation normal to the streamlines. This tall tube shows the stagnation pressure in the large upstream settling tank. The difference between this stagnation pressure and the static pressure at the upstream tubes gives a dynamic pressure of about 11 inches of water. At the middle of the bend, there is a pressure difference normal to the streamlines of about 3.5 inches of water. This is close to what we would predict using Euler's equation for the normal pressure gradient. Downstream of the bend, the pressure is almost uniform again. The slight variation there is due to a complicated secondary flow induced by the bend. As we increase the flow, all the pressure differences also increase, according to the square of the velocity. But the pressure difference due to curvature remains a constant fraction of the dynamic pressure. Another example of streamline curvature is the throat of this half venturi. The throat pressure at the curved wall is considerably less than at the straight wall because of the streamline curvature. When we use venturis for flow measurement, the pressure we measure at the wall is therefore not the average pressure at the throat. That is one reason for calibrating venturi meters. This bending of the jet toward my finger is the Coanda effect. A better experimental setup is this freely suspended hollow cylinder with a small static pressure hole connected to a manometer. Since the streamlines are curved, there must be a normal pressure gradient, with the pressure at the cylinder surface less than the atmospheric pressure at the outside boundary of the jet. The manometer shows that the pressure is less than atmospheric. Because of this subatmospheric pressure, there is a net force on the cylinder toward the jet. Now the manometer is balanced again. The Coanda effect is also part of the explanation for this.